This is the shell and tube heat exchanger calculator available at chemicalengineeringnow.com. This is a very broad-based form applicable to a number of different design types. That is, it applies to the calculations related to heat exchanger types such as double pipe, multi-tube, multi-pass, single phase or condensing phases with or without the presence of non-condensables, horizontal, vertical, or inclined tube arrangements, axial or cross-flow patterns in the shell, and our bare or low-fin tubes. The layout of the form has the tube side information on the left and the shell side information on the right side. With the process-related information at the top of the form and the exchanger-specific information at the bottom. This form is used in conjunction with the LMTD calculation form, which we shall see in a moment. The calculator generally solves problems in the direction that determines the required heat transfer area and fluid pressure drops. Although, as with all calculators at chemicalengineering.com, a quick and simple trial and error permits the calculation of any parameter of particular interest. Consider this example in which we have a heat exchanger available to us either in the yard or available as from a used equipment provider. And the question is, will it fit our requirements? Let's look at the process requirements first. We want to see if we can use this to cool 6,500 pounds per hour of liquid A from 180 degrees Fahrenheit to 110 degrees Fahrenheit with liquid B that is available at 90 degrees Fahrenheit. But we cannot allow liquid B to go over 120 degrees Fahrenheit at the outlet. So we will do a heat balance and calculate the required flow of B. Ideally, a closer approach in temperature would be more economical, but the 120 degrees is provided by our problem. Let's first notice that the fluids do not cross each other. First, we'll calculate the amount of heat that's transferred from fluid A. So fluid A transfers 152,425 BTUs per hour. That means the flow of fluid B will be 5,091 pounds per hour. The fluid parameters are all provided here on this form for fluid A and for fluid B on the inlet and outlet. For our calculation, however, we're going to have to know the average bulk temperature, the wall temperature, and the film temperature. So the average shell side bulk temperature is the average of the inlet and the outlet. So the 180 plus 110 divided by 2 is 145. Similarly for the tube side, the average is 105. The average wall temperature therefore is 145 plus 105 divided by 2 is 125. For the film, it's the wall plus the shell divided by 2 is 135, and on the tube side it's 115. You could either use these film temperatures, or a more conservative approach may very well be to use the bulk temperatures. Now the exchanger that is available to us, let's take a look at it. It has 2 tube passes, 16 carbon steel tubes per pass for a total of 32 tubes. The tubes are 20 feet long and have an OD of 0.75 inches, a tube wall thickness of 0.065 inches. They're arranged in a triangular pitch pattern of 15/16 of an inch. The shell side diameter is 8 inches. It has 19 baffles that are 12 inches apart, and there's only one pass on the shell. So we're going to try using fluid A on the shell and fluid B in the tubes. So if we first calculate our LMTD, we have 180 over cooled to 180 on the hot fluid in, cooled to 110. The cold fluid comes in at 90 and is heated to 120. There's one pass on the shell and 2 passes on the tube. The log mean temperature difference therefore is 20.56. LMTD is 20.56. So if we jump over and we input all of that data into our our form, we got the heat transfer rate, we got our LMTD, we have liquid in the tube, liquid in the shell, we have all of our shell, our tube side information, all of our shell side process information. We have a horizontal tube, we have our tube side information, our diameter, number of tubes, wall thickness, number of passes, I guess at our tube length, carbon steel material. We've applied a filing factor of 0.005 in this example. We're cross flow pattern in the shell, 8-inch diameter, triangular tube pitch. Our pitch is 0.9375 inches, 19 baffles, 12 inches apart, and again applied another filing factor. So our calculation will show the inside and the outside clean side coefficients. The overall coefficient U is 27.93. The overall heat transfer area is 265.5 square feet. Of course, we used 32 tubes, and the total length of the tubes would be 21.127 feet. So this exchanger is slightly small, but if we eliminated these filing factors, we would see that the exchanger would be 15.227 feet would be adequate. And we've also calculated the tube side pressure drop and the shell side pressure drop. So that's a quick example of how we can apply problems and use the shell and tube heat exchanger calculator at chemicalengineeringnow.com.